Hello all, my name is Ashutosh Rastogi. I'm a teacher by profession. My mission is to impart quality education for all. For that purpose, I'm creating these videos. If you appreciate my work, then please do like my video and subscribe my channel so that I could get the motivation to prepare more videos. Anyways, today in this particular lecture, we will going to discuss about adaptive delta modulation. These are the outlines. We'll start up with the introduction where we have discussed whatever we have learned in earlier lectures such as delta modulation and what are the various errors associated with the delta modulation. Then we will try to give a brief idea why do we actually need adaptive delta modulation. Then we will discuss the principle of adaptive delta modulation, which will be followed by the description of ADM encoder as well as decoder. Then we will going to discuss several advantages of adaptive delta modulation. Then we will going to discuss several differences between delta modulation and adaptive delta modulation. And finally, we're going to conclude via discussing some of the applications of adaptive delta modulation. So in our last lecture, we have discussed about the delta modulation, where we actually find that it is one of the most bandwidth efficient scheme in comparison to our pulse code modulation and differential pulse code modulation, since it is generating only single bit in order to encode one sample value. So delta modulation basically suffers with two types of errors. They are slope overload noises and the granular noise. This particular figure shows those noises that is happening in the delta modulation. This is our continuous time signal xt, and this gray portion, this portion is actually representing slope overload distortion, and this is actually showing our granular noise. So error signal is nothing but it is the difference between the staircase approximated value and the actual signal value. Since our approximated signal is not in a state to map the actual signal value, so this is actually being considered as the error. So we have already discussed that slope overload distortion will going to happen when the slope of signal variation is greater than the slope of staircase. So the slope of signal would have been given as it is the time derivative of signal variation xt, and the slope of staircase would have been calculated as total amplitude variation divided by sampling duration ts, that is equal to delta times of fs, where fs is nothing but it is the sampling frequency, which is the inverse of your sampling duration ts. So obviously, when does this slope overload distortion will going to occur or will going to happen? It will going to happen when the maximum slope of the signal variation is greater than the slope of staircase. I mean, the maximum slope of signal variation is greater than delta times of fs. When this condition is fulfilled, then this slope overload distortion will going to happen. And when this granular noise will going to happen, when the maximum slope of signal variation is less than delta times of fs, or we could say that when the maximum slope of signal variation is less than the slope of the staircase. So in both of the case, our staircase will not be able to map the exact signal values. That's why error will going to happen, and that error is nothing but is your delta modulation's error. So in the similar manner, granular noise will going to happen when the maximum slope of input signal is less than delta times of fs that we have already discussed. So the quantization error due to the slope overload and granular noise is minimized by making the step variation adaptive. So obviously, if the slope of signal variation is greater than delta times of fs, then slope overload distortion will going to happen. And if the slope of signal variation is less than delta times of fs, then granular noise will going to happen. So anyhow, we must have to reduce the error. If we can make the step size variation adaptive, I means if signal variation is high, then automatically the step size should get increased, and when the signal variation is low, it automatically reduces out its step size. So this is how we can limit our error. So how can we do that? So the solution is adaptive delta modulation. So now we're going to discuss the principle of adaptive delta modulation. This particular figure shows amplitude versus time graph of any signal, of any continuous time signal xt. These lines are actually showing the sample value of our signal where sampling duration is ts. So now what we're going to do is we're going to approximate our signal in the form of staircase. This is our staircase which is trying to approximate our signal as we did in our delta modulation. What we did in our delta modulation is there the staircase of the step size is remains fixed, that is equal to delta. But what difference we are seeing here is here these step size of the staircase are not uniform, they are changing. So let us say this particular step size is denoted by delta 1 and this particular staircase size is denoted as delta 2. So here in this delta 1 and delta 2, what relationships exist is this step size delta 2 is greater than this previous step size delta 1. So this is what we are doing in our adaptive delta modulation. Depending upon the signal variation, the step size is automatically changing. I mean, if the signal variation is very high or signal is very steep, it automatically increases its step size from delta 1 to delta 2. In this particular portion, when the signal strength is not pretty much high, it automatically reduces its step size in order to reduce the error signal. Just like our delta modulation, our 1-bit quantized signals would have been given as like this one. Here also all the mechanism is remain same. Just like in our delta modulation, we just only need to put these values of 1 bit, that is either 1 and 0. Here 1 represents the next step of the staircase will be positive and 0 represents the negative step size. So here how we are going to generating the bits is we will again going to take the difference between the current signal value with its previous version of staircase approximation. If signal value is greater than its previous value of staircase approximation, then 1 bit is generated like here, like here, like here. We are generating 1, and at this particular moment when the current value of our input signal is lesser than the previous staircase approximation, 0 bit is generated and so on. So here is how we are actually generating the bit sequence of ones and zeros. So bit stream generation is as analogous to or as similar to as our delta modulation, but here what the difference we are making here is we are making our step size delta adaptive. It can automatically increase or reduce its step size depending upon the signal variation in order to minimize the error. So adaptive delta modulation is the modification of delta modulation. We can say that, as we had already discussed, that its working is almost similar to our delta modulation, but we are in a state to reduce the errors that we have in our delta modulation. So the principles over which all the adaptive delta modulation algorithms are working on, they are as follows. Depending upon the output of 1-bit quantizer, that is if quantizer output is high, that is if 1 bit is generated, then the step size may be increased for the next sample, and if the output of 1-bit quantizer is low, or we could say the 0, then the step size may be decreased. So this is what we have discussed. So here one thing should be noted that the above set points are just the example rather than they are just the standards. So I mean obviously if 1-bit quantizer value is 1, then we're going to increase our step size, and if its output is 0, then we're going to reduce the step size. But how much we're going to increase or how much we're going to decrease, that has to be governed by certain standards. But in any of the adaptive delta modulation algorithms, we are following same procedure. So this particular figure shows the adaptive delta modulation encoder. So if we closely observe that this particular figure actually showing the delta modulation encoder, where we will going to have incoming input sample value in terms of x of NTS, which will get subtracted with the approximated staircase value of our signal, and that error signal will get passed through by 1-bit quantizer, which will going to generate some quantized value of signal in terms of step size, and depending upon that step size our encoder will going to generate certain bits, and this summer will going to have these two inputs. Number one is 1-bit quantizer signal output, and second is the previous state of the approximated signal, and with the combination of both these two inputs it will going to generate its current staircase value u of NTS. Here u of NTS is showing the current staircase sample value, and u of n minus 1 TS is the delayed version of U of NTS, or we could say that it basically represents the previous approximated staircase version of the signal. So this particular structure reflects the accumulator, which will going to retain the approximated signal value of our signal. So this is all about our delta modulation. So what is the difference, or what are the things that will going to make our delta modulation adaptive? So in adaptive delta modulation, what we have add on to our delta modulation is we have added another logic for step size control. This is the logic which will going to change or alter the 1-bit quantizer output. That is, it will going to make our step size delta variable. Whereas in the delta modulation, we have this step size delta fixed one. So the logic for step size control is taking input from the 1-bit quantizer output, and depending upon this value of delta, it will going to increase or decrease the value of delta. So here we will be having variable step size delta, which will going to pass through this summer, and all other process will going to remain same as we have in our delta modulation. So by default at the output side, we will be only going to have single bit outcome either in terms of 0 and 1 as we have in our delta modulation output. So if we closely observe the adaptive delta modulation encoder, we find that it is similar to delta modulation, but what it has in addition is it has the logic for step size control. That means with the help of certain logic, it will going to increase or decrease its step size. So the input to the step size control is the output of the quantized error signal, as we had already discussed, which will going to alter its step size. I mean, if the error signal is positive, it will going to increase its step size, and if the error signal is negative, then it will going to reduce its step size. Here accumulator output is the summation of the previous staircase value and the variable step size. So in combination of these two, the accumulator will going to produce the staircase approximated version of the signal. So in the steep segment of the input signal variation, the step size delta is increased in order to minimize the slope overload distortion. And if the input signal variation is very low or it is almost unchanged, then the step size can be reduced in order to reduce the hunting noise. So the adaptive delta modulator, it can take the continuous changes in the step size, or it could also take the discrete changes in respect to time. I mean, continuously the step size delta value will get changed, or at certain instance or at discrete time of intervals, it will going to alter or change its values. So this particular figure shows the adaptive delta modulation decoder figure. So it is made up of basically three parts. In the first part, we will be having input and the logic for step size control. So the major responsibility of this particular part is with the help of input signal, it will going to generate variable step size input with the help of this logic for step size control, as we did at our transmitting side. And then this variable step size will get passed through to the accumulator. So this accumulator, with the help of variable step size delta in combination with the previous staircase, it will going to generate the current staircase approximation of the signal. And when we will going to pass this staircase approximated signal through the low pass filter, it will going to generate a smoothen out output, which is nothing but our input signal as we had generated at our transmitting side. So this is how we will going to retrieve our input signal back. So with the help of input bit and the logic for the step size control, the variable step size is calculated using the same process at the transmitter. So we are using similar sort of functionality in order to generate the variable step size signal. So then it is fed to the accumulator, which then creates the staircase waveform, as we had already discussed that the accumulator, which contains the previous staircase approximation version of the signal with the help of incoming variable step size signal, with the combination of both these two, it will going to generate the current staircase sample version of our signal. So then that staircase approximation of the signal is passed through the low pass filter, which will going to reconstruct the signal and smoothen out the waveform. So some of the advantages of delta modulations are: signal to quantization noise ratio would have been improved in comparison to delta modulation, as in adaptive delta modulation we are reducing the slope overload distortion as well as the hunting noise. So obviously if we are in a state to reduce the noise, the signal to noise ratio would have been improved. So adaptive delta modulation has variable step size and its dynamic range is wider than the delta modulation. So obviously if the step size is variable, then the high variation are easily approximated with the help of adaptive delta modulation in comparison to delta modulation. So we can say that it is having high dynamic range in comparison to delta modulation. Or in easier words, we could say that we could map the signals which is having high variations with the help of adaptive delta modulation in comparison to delta modulation. So now we're going to discuss some of the differences between delta modulation and adaptive delta modulation. So the major differences are, in the delta modulation, the step size is fixed for the whole signal, whereas in the adaptive delta modulation, the step size is varies depending upon the input signal. So what we are achieving better in this particular adaptive delta modulation is we are in a state to reduce the errors that we have in our delta modulation. So the slope overload and the granule noise errors which are present in the delta modulation are not seen in the adaptive delta modulation. Obviously errors are there, but in comparison to delta modulation, they are very much less. Or we could say that in adaptive delta modulation, we have reduced out the errors that are present in delta modulation. So the dynamic range of adaptive delta modulation is wider than the delta modulation we had already discussed. Adaptive delta modulation utilizes bandwidth more efficiently than the delta modulation. Although both of them are generating the single bit outcome, but we are having better approximation in the adaptive delta modulation in comparison to delta modulation. So we could say that adaptive delta modulation utilizing bandwidth in much better way in comparison to delta modulation. Some of the applications of adaptive delta modulations are, this modulations is used for a system which basically requires improved voice quality as well as the high speed data transfer of the bits. Or we could say that where we required high data rate. So at certain places for television signal transmission, this modulation process would have been used. Then it is also being used for voice coding where we are actually requiring high compression with low noise power so that ultimately we could have high signal to noise ratio at the receiving side. So in a system called TriTac digital telephones, US Army Force have used 16 kilobits per second rates to conserve the bandwidth over the tactical links, and for improved voice quality they have used for 32 kilobits per second rates. So this is also the application of adaptive delta modulation where US Army uses this particular sort of modulation scheme. So it is also used to encode the voice signal in the Bluetooth services, such as nowadays we'll be having certain Bluetooth enabled devices such as speakers, Bluetooth headset, etc. So these are the various references that we have used in order to make this presentation. Thank you very much for your patient hearing.